Hello everyone. I am the session of this chair. My name is Vaibhav Sharma. I'm a PhD student under Dr. Radhika Barua at Virginia Commonwealth University in the Mechanical and Nuclear Engineering Department. So thank you for being here. We have our first guest speaker, who is Radhika Barua she's an assistant professor in the Department of Mechanical and Nuclear Engineering at Virginia Commonwealth University, Richmond, Virginia. Her technical background includes competency in alloy design, magnetic material processing using conventional and additive manufacturing approaches, and advanced material characterization using both laboratory and synchrotron probes. She holds a PhD and a MS degree in chemical engineering, specializing in material science from Northeastern University, and bachelor's degree in chemical engineering from Vishwariya Technological University in India. Her research interests focus on developing advanced functional magnetic materials and devices for diverse applications in the power and energy sector, including magnetic refrigerators, thermal energy harvesting devices, sensors, actuators for harsh environments, and permanent magnets. To the service to the scientific community, she serves as the chair of Richmond chapter of IEEE Magnetic Society and IEEE Women's in Engineering Affinity Group. So, Dr. Barua, floor is all yours.
Thank you, Vaibhav. That was quite a mouthful of an introduction, but yeah. All right. So, yep, the shift to the online conferences triggered by COVID-19 has definitely transformed the way in which we are disseminating research to the academic community. And so, having said that, thank you for inviting me to talk at the Around the Clock, Around the World 2023 conference. So, as Vaibhav has mentioned, I'm affiliated to Virginia Commonwealth University. And if you don't know who we are, here's a little 30-second spiel. So VCU, as we're known, is a public university. We are located in Richmond. That happens to be the capital of Virginia in the United States. VCU has a research expenditure of over $300 million per annum. That makes us a research intensive tier 1 university. We have around 226 degree and certificate programs, and we bring currently our enrollment is at around 30,000 students from over 110 countries. So we're definitely very global in character. And within VCU, I happen to be the principal investigator of the AM2P Lab, which is the Advanced Magnetic Materials Processing Lab. And what we do in AMP Lab is essentially we make magnetic materials. And so what we do is we make magnetic materials in bulk, film, as well as particle form for diverse applications in the power and energy sector. And that ranges from permanent magnets for energy conversion to microwave ferrites for 5G platforms, magnetocaloric materials for solid state heat pumps, as well as some magnetic nanoparticles for biomedical imaging. We are funded by NSF, the Commonwealth Cyber Initiative of Virginia, as well as the Commonwealth Center for Advanced Manufacturing at Virginia. And today I'm going to mostly focus on what is Vaibhav's research. Thank you, Vaibhav. And we will be mostly talking about magnetocaloric materials. And so a little bit of fundamental on what a magnetocaloric material actually is. So by definition, a magnetocaloric material is one that undergoes a reversible temperature change upon application and removal of a magnetic field in adiabatic conditions. Now, any magnetic material will do this. If you apply a magnetic field and remove it, it will undergo a temperature change. Even iron would do this. But it does that, the temperature change is very small. And so to see a pronounced temperature change, the magnetocaloric material must demonstrate a strong spin lattice coupling. And typically, this response is most pronounced when it occurs in the vicinity of a magnetic transition. So to explain this, let's look at a prototypical magnetocaloric material, a nickel-manganese gallium Heussler alloy. So the nickel-manganese gallium Heussler alloy at room temperature shows an L21 crystal structure, such as that shown over here. It is ferromagnetic at room temperature. Upon heating, it undergoes a Curie transition, so a ferromagnetic to a paramagnetic transition at around 360 Kelvin. And this magnetic transition is accompanied by a simultaneous crystal structure change from an L21 to an L10 crystal structure. So it's concurrent, and exactly at this magnetostructural transition temperature, if you were to apply a magnetic field and remove it, a magnetic field of strength 5 Tesla, you would see an adiabatic temperature change of around 8 Kelvin. And so this is a classical example of how a magnetocaloric material works. And depending on the temperature at which we see this magnetostructural transition, magnetocaloric materials can be used for a number of potential energy-related devices. So a magnetocaloric material that shows a low temperature magnetocaloric response can be used for hydrogen liquefaction purposes. Those that show room temperature magnetocaloric MCE effects are of interest tremendously for magnetic heat pump devices, so magnetic refrigeration. And those that show magnetocaloric effects at high temperatures can potentially be used for waste heat energy harvesting. But regardless of what the material does, in order to use the material to realize its true potential, it has to be deployed within an active magnetic regenerator device. So that is known as an AMR device. And I show a schematic of it in this slide over here. And note that the key component that we are interested in our research is this porous heat exchanger that you see over here, which is also called as the regenerator. So in ideal circumstances, in an ideal world, this regenerator is made entirely of a magnetocaloric material only. It demonstrates a large magnetocaloric response, which manifests itself as an adiabatic temperature change, that is a delta T, and a magnetic entropy change, that is a delta S, at moderate magnetic fields, that is around less than 2 Tesla, preferably. The magnetocaloric material should demonstrate high thermal conductivity, low heat capacity, high electrical resistivity to reduce eddy current losses, because within the AMR device, the regenerator moves in and out of a magnetic field. It should be mechanically stable, chemically stable. And from the perspective of manufacturability, it should be made entirely, if possible, of geo-abundant elemental constituents, so no rare earths. And it must be easy to manufacture with customized architectures that are porous. So a regenerator must have voids, because within the device, from a system integration perspective, it has to allow flow or passage of a heat exchanger fluid. Now, typically, regenerators are made either as particle beds or as plain plates that possess inherent challenges that reduce the theoretical performance when you put it in a device prototype. So, for example, if you have a packed bed with prolonged use, this leads to segregation of the particles, leading to pressure drop along the length of the regenerator. And in extreme cases, that can also cause flushing of the particles in the surrounding heat exchange media. The other way of making it is by making stacked plates using MCM composites. So these are magnetocaloric particles with binders, and they typically, because of the presence of the binder, they show a dilute magnetocaloric response, and they also have very strict geometric requirements. So for instance, the plates have to be less than 500 microns thick, spaced 100 microns apart. In ideal circumstances, are not very easy to make. So there are theoretical studies that show that regenerators with microchannels and pinfan arrays are better than stack plates, where they demonstrate cooling capacities that are quite high. And so if you have a microchannel regenerator geometry, we would ideally want it to be compositionally graded along the length. So note that when you have a magnetocaloric material, it shows at any given point, only a single part of the regenerator will experience the maximum magnetocaloric response. So this leads to the concept of a graded regenerator, where we stack up a number of magnetocaloric materials that have transition temperatures that are near each other, and it leads to an expanded working temperature range. Now, that's not very easy to make when you think of it. using conventional machining methods like, say, boring, milling, drilling, etc. This allows us limited control over the internal structure. So with this, we turn our attention to 3D printing. So we are looking into additive manufacturing schemes of regenerator fabrication in our research. And so what 3D printing is, it essentially encompasses several manufacturing technologies that build net-shaped parts, and they do it layer by layer. So there are 7 different types of 3D printing if you look at it, and they each vary in their form, or whether they are amenable to plastic or metal. They differ in their material selection and their surface finish, and the durability, and also in the manufacturing cost and strategy. But regardless, all these techniques allow us to get high quality parts with functionally graded design and less geometrical constraints. So that's what we want to do. And so in the literature, researchers have used direct energy deposition, binder jetting, and powder bed fusion techniques to make microchannel thin-walled regenerators. So here's an example of work done by the Fraunhofer Institute, where they have attempted to use powder bed fusion to make heat exchange structures. And so powder bed fusion is a technique where there's a bed of powder, and you fuse the powder by melting a selected region with the help of a laser. And so in this study, a base alloy of lanthanum iron silicides were used, and once the net shape channels were printed, they were subjected to heat treatment and hydrogenation using post-processing. And at first glance, when you look at it, their net shape samples look really nice. They show high delta S values of about 4 joules per kg Kelvin at a very low field of 1 Tesla. You can stack it up to form a cascaded structure. They have wall thicknesses of around 300 microns with channel dias of 600 microns. But then if you look close up in their SEM, you can see that the channels don't have uniform size. And upon post-processing, it also leads to molten particles within the channels. That's definitely not really wanted. Another method that has been tried by Oak Ridge is binder jetting. So here, there's no melting and remelting of the powder. What happens is we have a powder bed, and we have a binder that comes in, and it is dispensed. So it joins the powder layer by layer. And so the Oak Ridge group has been able to make microchannels with channel widths of around as small as 800 micron channels. But the smaller they get, they noticed that there was more clogging observed. And so with this, we turn our attention to 2 different methods, because powder bed fusion and binder jetting, they have their inherent problems, and they don't allow us to make compositionally graded multi-material structures. So what we're doing in our research is we're looking at DED, which is direct energy deposition, and direct ink writing. And so I'm going to go through some of our work results. And so the first is DED. So DED is essentially, it's a little different from powder bed fusion and binder jetting in the sense, here we have powders are fed within a nozzle, and then it allows us to make multi-materials structures, because the precursor powders are deposited simultaneously into a melt pool, which is created by a laser, and then we can draw the print head upwards. And so we've made cylindrical rods, honeycomb structures using this technique. This work was done during the very end of my postdoctoral research when I was at Northeastern University under the auspices of an ARPA-E project. And what we chose to do in the project is we focused on a lesser known magnetocaloric material, that is an aluminum iron boride, simply because of the very composition allowed us to use 2 different powders and 2 different nozzles. And so to test the concept of the feasibility of making a graded structure. And so aluminum iron boride is not as good as lanthanum iron silicides, but it shows a moderate magnetocaloric effect, a delta T of around 2.2 Kelvin. You can tune the delta S to 4.6 joules per kg Kelvin at 2 Tesla. And what we found is that we could make structures that were compositionally homogeneous using the operating parameters that I show over here, but it took us a while to optimize all the parameters. There's a lot that goes into 3D printing. Once made, the samples were multi-phased, so we saw a desired phase, of course, ALFE to B2, and a couple of other phases, which is very typical. You would get it even in a cast sample. And then following our previous guidelines from our studies on cast samples, the 3D printed samples were annealed at 1100 C for 72 hours. And it was observed that for the printed rods, they looked really good, but we couldn't get homogeneous samples in the honeycomb sample, printed samples, which was unfortunate. Commensurate with our results for the microstructure, we noticed that the 3D printed cylinders also showed good magnetization properties comparable to that of cast. So an M-sub-S of 74 EMUs per gram, TC of 305 Kelvin, and comparable delta S, but we've completely lost the delta S in the honeycomb samples. And to understand why this might indeed be the case, it's important. I have a video here. It doesn't seem to be playing, unfortunately. Well, if it did play, you would notice it was a pretty interesting video, because when you see it, you'll notice that the laser head doesn't move in one direction, or it doesn't raster. It moves in a very complicated fashion while printing the 3D printed structure, and that's by intention, because DED is intrinsically characterized by very large, so it's a non-equilibrium processing technique, large thermal gradients, high cooling rates, cyclic reheating as we're building layer by layer. And so path planning is very important. And while it's easy to make a rod, there's no path planning with it. When you have an intricate structure, that needs to be optimized quite a bit. And that's something that we are working on right now. But that is a big problem with DD, because melting and recrystallization of the magnetic particles tends to complicate the manufacturing process. For all magnetocaloric materials, such as that of AlFe2b2 shown over here, you have a very tight tolerance. So this is a pseudo-phase diagram of AlFe2b2, and only within these dotted lines over here will you see the magnetocaloric response. If you're off, you won't see it, because there's a very tight compositional tolerance to get the magnetostructural response. And so to do away with melting, recrystallization, and so on, we decided let's not move our focus from DED towards something which is more room temperature like. So we worked with direct ink writing. And so direct ink writing is essentially a 3-step process where first, instead of starting with the powder, we start with an ink. So we have our starting initial material is an LCMO powder that is combined with sacrificial binder with additives and a trisolvent resin to make an ink that flows nicely. We use that ink to get the structure that we want. And then once we've done that, we burn away the ink. We see some shrinkage happening in our samples, but what we end up at the very end is a consolidated metal part. And so that's what most of Vaibhav's dissertation is actually focused on. So he's been developing this direct ink writing work. And the advantages of this is you can get anisotropic structures with direct ink writing. So we have shown that you can put a magnetic field around the nozzle to get anisotropic microstructures, which would be great if you within a device. And it also, if you use different nozzles, you can also get a controlled chemical gradient. So with that in mind, we've done studies with magnetocaloric particles that are LCMO. So these are oxides, as well as lanthanum iron silicides, with the selection of binders. And then, of course, we have a patent on the ink where we worked with a certain ratio of 3 solvents and of an additive which is proprietary because it is patented. So the first thing we noticed is that shear thinning is, of course, desirable because we want the ink to flow uniformly through the nozzle. And so 83 weight percent and up works really well for us for the ink to flow. We can go to higher loadings of magnetocaloric materials, particles, but that has a tendency of clogging the nozzle. So that's also something that we are working towards. So this is something that we can optimize. And what we have demonstrated, so long as the feasibility to 3D print magnetocaloric structures with spatial resolutions as small as 150 microns. And this, and so the structures that we have are isotropic. And so when we see shrinkage also, within the microchannel structures, we see uniform shrinkage. So once the parts were made and shrinkage is observed during sintering, the sintering protocol was determined using DSC, that is a differential scanning calorimetry, and we found that 450 degrees is optimal to remove the binder. And so all samples were sintered first to 450 degrees Celsius, where they removed the binder, and then to higher temperatures to achieve densification. And so with the LCMO samples, so Webber has noticed that when you sinter the parts, he can get samples that have lost all binders, but still have the crystal structure of that of LCMO. So there's no degradation, thermal degradation that is observed. But his parts are porous. So you can see over here, I show the cross section of a computed tomography of a sample that was made by sintering at 1100 degrees Celsius for 4 hours, and it has around 20% porosity. So we've done some work on understanding how to control porosity, and we understand now that, of course, precursor powder morphology matters. So in our studies, LCMO powders are synthesized through a modified Pekini sol gel method. So in the sol gel method, it's a very easy way of synthesizing magnetic nanoparticles. And you can tune the microstructure by tuning the annealing temperature. And we can go all the way from 100 nanometers to microns, big particles, by just changing the annealing temperature during synthesis. And what we notice is that larger the particles, greater the magnetocaloric response. And so we made batches of samples with different particle sizes and 3D printed them. And here is a tomography. I showed the tomography of the particles, and you can see that larger particles are, of course, show less porosity, and smaller particles show around 20% porosity. So in the as printed samples, porosity decreases with increase in particle size. And counterintuitively, surprisingly, we noticed that this is not observed in post printing. So when the particles are small, when we sinter them, we can see that a reduction in porosity. So it goes from 20% to like around 4 to 3%. But when the particles are big, microns big, after sintering, we see an increase in porosity, which was a little surprising for us. But then we thought about it, and we realized that this is likely due to the inability of the larger particles to plug the pores that are created by the binder removal. So probably in order to optimize porosity, it would be best to use a combination of small and large particles, a hypothesis that we are working towards validating right now. We also then we looked at the magnetocaloric response of our 3D printed test coupons, and we found that the T sub T as well as the delta S of the sintered parts were definitely larger than that of the precursor powders. But then porosity also plays an important role here. And porosity, typically, if you have large particles, your samples show smaller delta S or MCE properties than that of parts made with smaller particles. And so that's the conclusion that we have right now. And we're still trying to optimize porosity and magnetocaloric response. And of course, LCMO was a starting point. We would like to try better magnetocaloric materials with enhanced response, even in the particle form. And it would be best to have a spherical morphology, because that is the gold standard for additive manufacturing. We want spherical parts. And so we've tried working with gas atomized LiFeSi powders that were obtained from collaborators at Ames Lab. And although it was great to 3D print them, and it is indeed possible to do it, sintering just destroys the magnetocaloric response. And that's partly due to oxidation and partly due to carbon contamination, because the carbon in the binder, LiFeSi is very sensitive to chemical effects. And so the carbon in the binder can interstationally sit in the lattice, and it's messing with the magnetocaloric properties. So in summary, we've shown that DED and direct ink writing are both amenable to a certain extent for fabricating graded thin-walled regenerators. Of course, there's work to be done. We are working towards replacing PO in the binder to minimize traces in the samples during post-processing. There are also some experiments that we have conducted in collaboration with University of Virginia at the 2BMB line at Oregon National Labs to understand how the binder is leaving the system in order to, and how that is affecting porosity. So it's all work in progress. Our DED work is also still being continued in collaboration with CCAM. This is a new project that we have started, so work in progress. Watch out for more results. So I'm going to end by saying thank you to the students who make this research possible. Definitely the chair of the session, Vaibhav, is right here. This is all his research. So thank you for your time. And if you have any questions, I will be happy to answer them.
Thank you, Dr. Barua. We have one question for you in the chat, actually, from Mr. Mahmood. Can you please compare between advantage of ALFEB and LAFESI as MCM for future commercialization, which is close to room temperature magnetic refrigeration?
So this is a very interesting question. LAFESI is definitely gold standard. I mean, there is no question about it. There's a lot of research that has been done by Oliver Good-Fleischer's group on the LAFESI system. The LFEB system is interesting. It's rare earth free for sure. I have extensively studied it in my work. We've looked at it from all perspectives, from the perspective of not only magnetocaloric response. It has an anisotropic thermal conductive effect, which is very high. Thermal conductivity, low specific heat capacity, very good mechanical and chemical stability, better chemical stability than LAFESI, if I dare say. It is promising, but we will have to figure out how to get the delta S of ALFEB high. And that's something I think can be achieved with chemical doping. There are papers where I've shown that if you add gallium or germanium, and I think some work where they've also shown that if you add silicon, you can tune it to higher temperatures. So with further research, it may be comparable, but not at this moment right now.
We have two more quick questions. So one is about does the delta T change with the shape that you are printing?
Delta T. We haven't measured delta T yet. We've just measured delta S as of now. I mean, we could do indirect measurements to get to predict the delta S after doing heat capacity, but that's not something that we have directly measured. It is of interest to us, for sure.
And the last question, is it possible to produce these samples through direct ink writing without the requirement of a sacrificial polymer producing composites? And if you had the chance of performing direct measurements on any of these systems?
So we haven't had a chance to do direct measurements on any of the systems. Most unfortunately, we don't have the setup in VCU. This is something that I would love to do. And we're looking at collaborating on it with other groups. Having said that, this is a nice question. Can direct ink writing be done without a sacrificial polymer? Unfortunately, that's against what direct ink writing is. We need an ink. And so to make it flow, you have to put the magnetocaloric powders in a sacrificial polymer. And so producing composites, we can form composites. I mean, if you just, so let's put it this way. If you make, after we have 3D printed it with the composite, it is a magnetocaloric material for sure. I mean, we can measure the delta S, it will be dilute. We have done that. The dilution of the magnetocaloric response is commensurate with the amount of particles we have in the composite. But then again, I think if you have a composite like that, its mechanical strength will definitely not be comparable to that of a like a solid metallic part. So it is not of interest to us. There are some papers done by a Franco-Victorino's group where they have made composites with FDM using 3D printing. They haven't shown channels yet, but they have done it. But what I noticed in that work too, they haven't removed the binders. But if you don't remove the binders, you will always have a diluted effect. And what does that do to the mechanical stability? That's something to be seen.
All right, without taking more time, thank you, Dr. Barua, for your time.
Okay, thank